Hey there, everyone. My name is Ryan. Welcome to my channel, and thanks for tuning in here today. So, I want to talk about optimizing bike scooter rebalancing plans for shared mobility. Okay, so I'm going to focus on a few different systems, one in New York City, one in Nashville, Tennessee, and one in Portland, Oregon. They are all owned and operated by different enterprises. So, in in New York City, we have Citibank. They kind of run the show there with all the Citi Bike bikes, I guess. And Nashville is a different system. I'm not sure who runs that. I worked there years ago. I kind of got acquainted with the thing, but that was a long time ago. I forgot. Portland, I think, is actually run by Nike, however you want to pronounce that thing. You can Google the one for Nashville. I don't know who owns that. We can actually Google that right now. Let's see here. Bike biking system, bike share, bike share system, something like that. Nashville B cycle. Okay, so it's called B cycle. Okay, so that's fine. So I want to take a look at how to optimize these types of plans, and there's others around the United States too. I set this optimization routine up so you can go ahead and plug in different cities. I'll show you how that works in a couple of minutes, and it's going to run or go in and fetch different data sources, right? Usually these are in JSON format, so JSON, JavaScript object notation, and that's going to fetch it and bring it into the model. The model is going to run and show you the optimization planning for rebalancing all the scooters or all the bicycles. A lot of these programs maintain bikes, but some of them actually maintain scooters too. I've seen both. I've seen both in Nashville. And we're going to look at how to do this very, very efficiently. So I have heard, or I Googled this anyways, I Googled this and I found out that Citibank actually does have some kind of optimization, performance, data-driven solution for the Citi Bikes program. So I applaud the effort. I know some people that work at Citibank and I know their jobs are completely not optimized and everything is manual and task-driven and very time-consuming. I used to know a guy that would work there. Oh my goodness, this guy would take like 40 hours to do something I could literally do in 15 to 20 seconds. I don't know whatever happened to that guy. But a lot of things in Citibank, based on my observations, are not optimized. But if this is, based on my Google search, it sounds like it is. I applaud you for it. I think that's great. I think that's fantastic. So let me show you how to do this. And I did a Google search to see how Citibank is doing that. They don't expose that, right? So that's proprietary. That's shared only, like it's an elite inner circle, Illuminati or whatever. I know how this thing actually works. But I'll show you how to create your own based on their real-time data. So they do give you the real-time data. You can ingest that into your own system. I set up an optimization system and we can experiment that and see how that works. It's probably analogous to the way that they're actually doing it, maybe slightly different. When you get into the optimization world, there are similar ways to do things that are slightly different, but the outcome is pretty similar. So I'm guessing it's going to be kind of like I'm going to demo here. But again, like they don't expose how it's done, so I really have no idea. But even before we get there, let me take a step back and say, why would you even want to do this type of exercise, right? Why do we want to try to understand bike or scooter or both? In this case, we're going to look at bike sharing. Why do we want to look at bike sharing optimization or scooter rebalancing optimization or both? Why do you want to do that, right? So in a shared system like Citi Bike, it's just more efficient, right? It saves time, it saves resources, it saves gas. These guys have to drive around in a truck, load all the bikes onto the truck. If you have a station that has a whole bunch of bikes and redistribute them around the stations that don't have a whole lot of bikes, right? So if they drive the trucks in an efficient path and do the rebalancing in an efficient way, it's going to save them a ton of money, right? Who doesn't want to save money? Who among you, or who do you know, that doesn't want to do things faster? Okay, I don't know anyone that doesn't want to do things faster. Pretty much everyone wants things faster, right? And who wants to spend more money to do something, right? If you can save money and do it faster, everyone's going to pick that, right? Why would you want to do things slower and spend more money, right? Nobody wants it. So that's why we do these optimization routines. That's first and foremost. So operational efficiencies, cost reductions, these are the obvious things, right? If you do this in a naive way or just basic random rebalancing, I guess it's kind of good. But again, if you don't optimize the process, you're going to spend more money and spend more time. Who wants to spend more money and spend more time to do something that you can save time and save money? It doesn't make sense, right? So demand responsiveness, you have to demand reply to or respond to your customers' needs. So it helps Citibank in terms of saving time, saving money to get the same job done that they have to do no matter what. And it's better for the end user, it's better for the customer. Like I will admit, I don't use the Citi Bike program. I have my own bike and I use it quite frequently. I go biking almost every day if the weather permits. I don't use the Citi Bike program, but I think it's a great idea. Um, so if I was a customer, I would want the bike there. If I go there, I'd want to see the bikes, right? So it helps Citibank, it helps the bikers, right? So everybody wins. It's win-win. Environmental and sustainability purposes, right? Again, save time, save money. Trucks are running all over the place. If you can reduce that and eliminate some runs, go for it, right? Why would you not do that? Of course, you're going to do that, right? And this is not just New York City Bike. There's a few other competitors in this space. I don't know how much they really compete, to tell you the truth, but a couple other like service providers, I'll call them. I don't know if they're direct competitors and if they are cannibalizing each other's business. I'm not sure about that. But there's a few different entities that operate in this space. So NYC City Bike, I think, pretty much dominates. They seem like the biggest player in the market. There's one called Lime. I've seen that. Spin, I think I have seen that. Bird. So I Googled this and came up with this. Not sure what this is, but this did come up on the radar. So I guess apparently it's something called Bird. So all these guys are kind of in the same space, right? And based on my preliminary Google search, they all kind of partake in some kind of optimization routine, either in real time or close to real time, or they do batch processing overnight and probably roll trucks very early in the morning. I'm just guessing here, maybe 3, 4 o'clock in the morning, maybe 5 a.m. Not sure exactly the timing. But if you're doing it once a day and batch processing overnight, you might roll the truck at 4 a.m., do the replacement of the bikes when the traffic and utilization is down, and redisperse the bikes or reallocate the bikes at that point in time. But it helps all of these guys, right? So New York City Bike, Lime, Spin, and Bird, whatever that is, increase bike availability by 15% and reduce unsatisfied trip requests by 25%. So again, win, win, win. Everybody's winning here, right? So that's why we do this type of thing. So let me hit Control Enter. I am going to look at NYC City Bike. Of the three, NYC, Portland, and Nashville. And again, you can look for different markets. There's these GBFS files, all JSON, right? So JavaScript Object Notation, that's what it stands for. You can download these things from the source, get these actual JSON files, which are updated almost in real time, like minute by minute. I don't know if this is actually second by second, like you would see a stock ticker updating, from Yahoo Finance or any kind of source, if you have Bloomberg or something like that. I'm not sure if it's updating like second by second, but I'm pretty sure it's minute by minute for most of these guys, right? So again, applaud the effort. I think that's great. I think they're doing the right thing there. So this is just 3 examples that I'm experimenting with. If you want others, go ahead and search for those, GBFS, and you would need the name of the system. So like I said before, Nashville is called B-Cycle. Portland is called Bike Town. So I think that was operated by Nike or Nike, whatever you call that thing. That's what it was like a few years ago when I was there. That was back in, that was like almost 10 years ago. So it could have changed. I doubt it. Probably still the same thing. So anyways, let me run the code. I'm going to look at NYC first, and we can check out the other 2 markets, see how those measure up to the NYC. Definitely New York is the dominant market for these type of things. I mean, it's the biggest city in the United States by far. So you can imagine like it's a pretty complex network, right? And if you can understand this system, you can understand the other 2, Portland and Nashville, pretty easily. So let's start with the most complex and just work towards the easiest. If you don't get it at first, that's okay. NYC is a beast. And that's fine. So I put in a couple easier ones, Portland and Nashville, that we can take a look at, and you can experiment with those, right? If NYC is a little bit overwhelming. So we do want to set up a couple basic, these are called what? Not criteria, but different properties, and just based on these properties or parameters, I'm feeding data into the model and saying there is going to be a cap of 2,000 stations for Citi Bike. So I think how many stations they actually have? 1,500, I think. Citi Bike station, I think they have like 1,500 or so. Oh, 2,200. Oh, over 2,200. So we can actually up this even higher. I can say 2,500, right? So we're going to capture everything in the whole system. Now, that is just based on my Google search, and I would just have to guess like the bike station has to be operational and not damaged. I've seen some that are kind of out of commission. I mean, I've walked by some that that thing cannot be working. I mean, it's just demolished. So maybe if the system isn't functioning, it's not going to get signals uploaded right to the server in real time. So I don't know how many stations are actually in use, but I'll just say 2,500. I think we'll capture everything. It should be under the umbrella of 2,200 that I just saw. So I'm putting these parameters and I just ran the model. So I think we're fine there. Again, we're going through these different systems, grabbing this real-time data, updated minute by minute. I created a few UDFs over here. So this is a user-defined function. Again, to go fetch the data. If we need to do some cleaning, look for the right language, make sure that this is in English. So unfortunately, I only speak one language. I grew up in America. A lot of Americans don't speak any other languages, right? That's just the way it is. If you grew up in Europe, you probably speak 5, 6, 7, 8, 9, 10. I don't know. In America, it's not like that. Maybe you get 2, maybe you get 3 if you're lucky. I think for most people, myself included, you speak 1 and that's it, right? So fortunately, that is the most common language in the world. So I can still function pretty well in this country, of course, and if I go out of the United States. But English by far is the most common language. I think Chinese is number 2 and Spanish is number 3, but that's going way off in a tangent there. We don't have to talk about that. So we go ahead and fetch the data. We convert the JSON to, we're doing the request. So we fetch it right here. Literally the fetch is done right here. And we convert that to something that we can actually read and interpret, okay? So JSON comes almost like a machine learning sort of presentation layer to the data. I would say like the presentation is kind of machine oriented. Yeah, here's a good example. This is what this stuff looks like. So, oh, they do have a pretty print. Okay, so that doesn't help too much. Okay, but when you look at this, does this make any sense to you? Because it doesn't to me. I don't know what this is, right? When I click this button, does it make any sense to you? It makes no sense to me. I don't know what that is, right? But when you do the fetch to the system and you go ahead, pull that back and interpret that JSON string, which by the way is very easy for a machine to read and very fast, very quick. So you can do your uploads, your downloads, your fetching very quick. That's why it's converted to JSON, right? So for the machine, it's very easy. For the human, it's next to impossible, but we'll just convert that from JSON into a human readable format, right? So I have a couple different functions down here that go ahead and normalize all the data. So we're taking something intended for machines to consume and normalizing it so a normal person can look at this and say, oh, I think I know what this means, right? So that's the point of that. So we go ahead and parse some of the data. We're getting longitude, latitude coordinates. So I love working with lat long coordinates. This kind of came up on my radar maybe about 8, 9, 10 years ago. Before that, I never even knew what a lat long coordinate was. I majored in finance. I got my master's in finance. We don't study lats and longs in finance, right? You don't see that. It just doesn't exist, right? So I never had it in school, but after graduation, I kind of like stumbled across this thing and I thought, wow, this is cool. I like it a lot. You can plot anything in any part of the world, right? Using lat long coordinates. There's a whole system. The more precise you go after the decimal place, it goes from several meters to 1 meter to centimeters down to millimeters and so on. It goes more and more precise as you go further right of the decimal place. So I thought that was interesting. I started learning about that. So I think this stuff is pretty cool. So I take all of this, right? Take all this and convert that into a data frame where we have the ID of the what's it called, like a bike station, I think. I'm not sure if that's the official term, but the bike parking spot, right? The station, I guess. So you have an ID, you have a name, lat long coordinate. So with the lat long coordinate, we can identify anything on planet Earth, like I just described. Very, very useful. If you use just an address and say, well, the bike station is at this address, that's helpful. But again, for computers, for machines, for very precise type of analysis, I think a lat long coordinate is better. If you really wanted to convert these to addresses, you can actually take a lat long coordinate and convert that to an actual street address. And it's interesting to note you can actually convert a street address to a lat long coordinate too if you want to do that. Okay, so that might be helpful. In this case, I'm not doing that. I don't think that's going to help too much. Inventory shows us the overall number of bikes that can exist at that station. I keep calling it bike station. I hope that's right. I'm not even sure. And the number of bikes docked. Okay, so how many bikes are available and the docks. So I think docks in this case refers to all the parking stations for the bike, um, the bike parking um, contraption, whatever that thing is, and the number of bikes available there, right? So if it has a capacity for 30 or 25 or 50 or whatever, that is going to be the number of docks. The inventory could be the same number, can't be more, right? Because you can't park more than you have space allocated for that. But the inventory could be less. You could maybe have 30 docks at the bike station, maybe just 5 bikes, right? So that is going to be very interesting for this type of analysis, because if you have 30 spaces, only 5 bikes are there, you are really underserving the bike community, right? Because if 5 people come and take 5 bikes in the next 5 minutes, you're out, right? There's nothing there, and there's no guarantee that someone is not going to come along with the bike and park at that station. That's why they do the rebalancing, right? That's the whole point, to optimize the system, rebalance the bikes from concentrated areas to spaces that are less concentrated. You can imagine if there's a couple major office buildings close by and there's a bike station, there's probably a lot of people going into that bike station in the morning, commuting into work, parking their bikes, and hitting the up button in the elevator, whatever, and going to work, right? At the end of the day, people are coming out of the office, streaming out, going for the Citi Bikes, taking away, and going home, right? So the bike station could be all filled up at 9 o'clock. You probably want to redistribute some bikes, right, to other stations that have way fewer bikes and need some. So they're constantly doing this rebalancing, right? So that's the need here. And the whole point of this video is to optimize the way that's done, right? So you don't just randomly take bikes from one place and redistribute them to another, but you do this in a method or fashion that's efficient based on the number of bikes, right, that are there right now. And again, this is updating all the time, in real time, every minute. New data is being uploaded to that server and saved as JSON strings, right? So the server is measuring the number of docks, how many potential parking spaces are there, and how many bikes are there, right? So I hope you understand. It's kind of a complex problem, not too bad. We're going to solve it in just a minute. But it's not just very straightforward and very simple, right? There is a level of complexity here that we have to deal with. That's why we're doing the rebalancing and optimizing the whole process. Okay, so hopefully that makes sense. So there we go. So we have all the stations, the IDs, names, lat longs, the geometry, the X and Y coordinates, the capacity, and then the inventory of these stations, right? So that's what we're getting down here. And I'm going to go ahead, feed that into the model. So the model says, okay, so we have a capacity for 30 or whatever it is. I'll say 30 in this example. 25 bikes are there. We can leave that alone. If we only have 5 bikes and we have room to park 30, maybe we should bring over 5 or 10 bikes to that location and kind of balance it out a little bit. Again, if 5 people come and take all those bikes, it's going to be completely empty. Then the next person comes, can't rent a bike, and it's going to be inconvenient for them, right? They don't want that. So again, we try to satisfy the needs of Citi that maintains and operates this whole thing, this whole system, this whole network or infrastructure, whatever you want to call it, and the bikers too, right? So it's better for Citi, it's better for the bikers. Win-win when we do this right. So we go ahead and set up the the optimization down here, and we're going to look for all the bikes available in these rows and look at the XY coordinates, okay? So what bikes are on what stations? How full are these stations based on the capacity? Can we reallocate more bikes to this station or can we not, right? If it's pretty full, we probably shouldn't be putting more bikes. You don't want 100% of the bikes in the station, right? You want it mostly full rather than mostly empty, but you don't want it completely full and you certainly don't want it completely empty. So the way we're going to solve this is looking at K nearest neighbors. We're going to look at which bike docking stations or bike parking stations, I'm not even sure what it's called, look at which ones are full, mostly full, kind of full, not too full, right? We're going to look at these different combinations and look at other bike stations in close proximity to this. So we're using a K nearest neighbor model right here, or solution for this problem, okay? So I have several videos that describe how K nearest neighbor works. Take a look at those videos, or just Google it. Go ahead and Google it if you want to see how that works. Basically, you're looking at a like a collection of bikes, almost like a not really a network, a cluster of bikes. I would call it a cluster of bikes in a given location, right? And which ones are close to other bike parking spots? That's going to be a cluster. And you're looking at your nearest neighbors, okay? So that's the concept. Looking at a specific cluster and seeing how close or how far away other clusters are. The ones that are closest are clustered together, and the ones that are further apart or are just not neighbors, right? Those are not neighbors. Okay, so that's the concept here. We're going to set a pickup spot and a drop-off spot as well. So when we solve this problem, again, we are reallocating bikes from stations that are mostly full to stations that are less full and trying to balance out the distribution of bikes pretty evenly across the entire network. So that's what we're achieving here today. I think I just ran this before, but I was talking for so long. Let me just rerun it just to make sure. I think we're all set, but let me just rerun this thing too. So, so we did the K nearest neighbor reallocation of bikes, right, to see which bike stations are the most full, which ones are the most empty, and we're going to try to balance those out. And again, this is all real-time data, updated minute to minute, and it's coming from the actual Citibank server, or Nashville, right, for those other bikes, or Portland, Oregon. We'll go back and look at those two in just a minute. So I'm going to plot all the results on the Folium map. I'm a big fan of these Folium maps. I use this in a lot of my videos. It shows you street level views, all the names of all the streets based on lat-long coordinates for New York City. We're looking at NYC at this point, but all over the United States and all over the world too. So Plotly is a really great resource. If you haven't used it lately, I would encourage you to use it. If you've never used it, I would highly encourage you to do some research and figure out how this stuff works. You are going to learn a ton, and there's so many applications for this, you have no idea. So I just ran this. Basically, this is my output right here. Okay, and I ran this a couple hours ago. So when I ran this before, and again, every time you redo this, it's going to be a slightly different output because people are using these bikes all day, every day. A lot of it is really commuter time or rush hour time. So around 8 to 10 a.m., you'll see a big spike up. I analyzed Citi Bike data utilization, and you can check that out on my channel. I have a video put together a while back, 8 or 9 months ago, I'm guessing. I forgot the date, but it's out there. You can take a look at that. There's a big spike up in the rush hour morning commute, about 8 to 10 p.m. There's a big spike up about 4 p.m. to 6 p.m. Again, right around the rush hour, weekdays, weekends, it's all over the place, right? Because you don't have work for most people. It's 9 to 5, Monday through Friday. Weekends are off, again, for most people, but some people work on the weekends, right? So some people are using Citi Bikes 24/7, right? The system works 24/7. These bikes are always being updated in terms of which bikes are where, what's the capacity, what is the number of bikes docked at that station, things like that. So every time you run the algo, the output is going to be a little bit different because the server is constantly picking up new information, and you're fetching the updated data and making your analysis based on that. So every time you run it, it's going to be slightly different, but it should be somewhat similar generally. Again, the exceptions will probably be like the commuter rush hour in the morning and in the evening. We can see here it shipped 3,257 bikes were shipped. So that's quite a bit, right? 3,257. Surplus was 7,670, and the deficit was 8,421. Um, Quantity was 808, and the distance of kilometers. So this is the truck driving around. So that's a lot of moving around for the truck. That's why we're trying to optimize this thing and trying to help the people that manage the truck or drive this truck to do this in an optimized fashion. Again, like I said a couple of times, save time, save money, and provide a better service for the end user, which is the person that pays for the service, right, to rent the bike. That's what that is. So the plan changes every time it runs because the data is always updating, right? Citi Bike is running its own logistics and doing some kind of probably supply chain optimization routine similar to what I'm doing. Again, they don't expose how they're doing this, so we don't know exactly, but it's probably going to be very similar to the way I demoed here. It can be slightly different, but the results are going to be pretty much the same. So loaded locations, 1502, surplus, 7308, deficit 8830. So that is off a little bit, but again, the data is updating all the time. So if you do this 2 times in 1 minute, you should get the same results. If you do this and wait 5 or 10 minutes, the results are going to be a little bit different, right? So total bikes shipped, 2,800. Coverage needs 2,800 over 8,800 is 32%. Coverage available is about 39%, and post-ship violation 0. Okay, so we're fine there. So nobody ran those bikes, and as far as we know, at least based on the data, nobody's looking for a bike and they can't find it. So I think we're fine there. So what else? So mean inventory average per bike station, about 7 bikes. We can round up. There's no such thing as 6.99 bikes. Okay, that simply doesn't exist. Shipment stats are in kilometers. Again, the truck drove quite a bit there, 808 kilometers, just approximate. I don't know exactly how to do kilometer to mile. I know it's like, I forgot what it is, 0.6 or something like that. Divide by 0.6, multiply, I forgot. But it's probably like 500 miles, give or take. So that's a lot of driving for one day, but there's a lot of stations, right? Then we just see it's 2,200 stations that these guys have to manage. So pretty extensive network. What else? Maximum distance to move a bike, 1.52 kilometers. So you can tell they're not moving these bikes really far. Again, because of the nearest neighbor algorithm, you don't have to move a bike like 10 kilometers or 20 or 30. The whole system probably spreads out. Probably the diameter of this thing is 30 to 40 kilometers, I bet, end to end. If you look at the north-south diameter or the east-west diameter, probably pretty extensive. But the goal is not to take a bike from the northern boundary of the Citi Bike area and redistribute to the southern boundary, right? When you move these things, it's going to be short distances. You're moving from one station, maybe a couple blocks down the street, right? So most of these are going to be pretty short. 1.52 kilometers was the longest. That's probably, was that miles? Not even a mile, right? But it's interesting to know that there was kind of a longer move here, but the average move is 0.22 kilometers. So again, probably most of these bikes are moving from one block, 2 or 3 blocks away, right? If you have a lot of bikes parked at one station, you probably move 2 or 3 blocks north, south, east, or west to another station that doesn't have too many bikes, right? They have fewer capacity at that station. So you reallocate some bikes with a lot of capacity to a station with lower capacity, and on average it's 0.22 miles, maximum 1.52. So that makes sense to me because of the KNN algorithm. So let me open up the result here and we can see what this thing looks like. So if I go over here, everything saves to my default spot where I installed Anaconda, and it goes over here. So it goes users Ryan underscore. I'm not sure where the underscore came from. I never figured that out. Somehow when I set the computer, it gave it a name. I must have hit the underscore accidentally because I shouldn't really have that. But anyways, it's going to go to users and then your name, whatever you name the spot where you install Anaconda. That's how that works. So let me get the Citi Bike HTML file here. So you can see this is what it looks like. So you can see they actually operate in Jersey City. I just found this out recently. I did not know that, but that's interesting. You can see this pretty much represents the map of Manhattan. Right over here is Bronx, so that's a little bit north of Manhattan. Over here is Queens, that's where I live, and down here is Brooklyn. Okay, so if I look at these Citi Bike locations, I know a lot of these in Queens. I know this one down here. I know this one over here. I know that one. I know that one. Uh, I didn't even know there was one there. Okay. I know this one over here. I know exactly where that is. And I know this one over here. I know most of these things. Okay, so this all makes sense to me, right? If we go ahead and click here, we can get rid of the stations and then just look at the lines. These are the shipments or the movements back and forth between stations with a lot of bikes and stations with not too many bikes, right? So the lines represent the movement of the bikes and the dots represent the stations. Okay, so hopefully that makes sense. There's that JSON data that we saw before. And so I printed that to my default Anaconda install area. So it's going to be users, the name that you give it, probably not Ryan, although maybe it could be. And if I open the CSV file and drag that over, everything is saved to the same spot. So this is a station ID. It goes from this station to this station. The number of bikes moved was 1. I can pretty much guarantee the truck is not just picking up 1 bike, but they pick up 1 bike and drop it off at this station, maybe go to 1 down the street, drop off 2, and then maybe they have 5 over here, 17 are dropped off over here, 9 and 19. So we have the counts of the bikes, the station from, the station to, and then the distance and kilometers too, okay? Distance in kilometers. And you can see most of these are pretty short, right? It's not going too far. And you can see a lot of these stations are pretty close together, right? Like they're transferring the bike from from this station over here to this station over here. Okay. Apologize for all the coughing. I have this congestion for like 10 years. I cannot get rid of it no matter what I do. It's acid reflux and it just doesn't go away. So so that's the thing. We have the quantities, we have the distance, the bikes moved, so that's all helpful. Local pairing, that's what we're using the K nearest neighbors for. So finding the nearest neighbor, redistributing the bike. If you have a surplus of bikes or a whole bunch of bikes in one station, not a lot at another station, there's going to be a move, right? We're moving bikes from overpopulated spots to underpopulated spots, right? I like this view over here, like these arrows. I think that looks nice. Okay. And again, we're going from pairing choices, higher ship counts, to lower counts, right? And fewer receivers, to areas that are going to be utilized more, again, to satisfy the community of bikers that expect the bikes to be there. If you go to a station, there's no bikes, that can be frustrating. Again, I don't use Citi Bikes, so I don't use the service, but I can imagine if I did and I want to get a bike and I can't get it, that's kind of frustrating. And you want to prevent that from happening, right? So the green dots mean donors, these are surplus. The red dots mean there's a deficit, so that's a receiver station, right? And we saw that before. So green, there's too many bikes here. They go into stations that are red, okay? You can see the distribution here. So this is green to red. Here's all the details of the station. We have the station ID, the target, the surplus, deficit. So 0 surplus, it's down by 13. So it doesn't mean it has negative 13. You can't have negative 13 bikes, but it should have on average a higher number of bikes to keep this kind of balanced out, right? So it's going from, where is it? From this station right here over to the red, the green. Again, you have too many bikes going to the red. Capacity is 46, inventory is 40. So this station basically can hold 46 bikes. They have 40. That sounds like it's just too many, right? You have 4 bikes missing, but it's pretty fat. These guys are filled up with bikes. You can sacrifice 20 bikes right here. And that is just going to help you, right? So it's going from this station to this station over here. Okay, and So we have the capacity is 50, inventory is 9. So you can see that that's why it's red, right? So it can hold 50 bikes. It only has 9. You're missing 41 bikes, so it's mostly empty. That's why the truck is recommended to pick up 20 bikes from this station, right? It can hold 46. It has 40. 20 bikes should go from this station over here to this station. I'm just guessing the distance is maybe 0.2 kilometers, give or take, maybe 0.3 kilometers. It's not too far. You can see this is an easy move. The truck's going to pick it up, probably drop those bikes right in the back, ship it down the street. It's picking up from Broadway and Washington Place, and it's going to 2nd Avenue and East 6. And if I look at Google Maps, Broadway and Washington Place, let me see if I can find this actual thing. Oops. Broadway and Washington Place. Okay, Google Maps will take us right there. It's looking pretty good, guys. Looking pretty good. So where's my Broadway and Washington Place? Is that it? See Broadway. Washington Place. Okay, so I'm going to go to the street level and see if there's actually a Citi Bike bike station or bike parking lot, whatever these things are called. Let me see if they have this thing over here. Oh, they have it right there. So look at that, guys. Perfect, perfect. We got that. And it's still pretty full. Look at that. What is it? Held 46 bikes, and it's pretty full. So I think somebody's sleeping right now. All right, it can hold 46, and that one looked pretty full. It has at least 40. Now, this is not the picture of that, right? Google Maps was probably done months ago. Sometimes I'll show you like the time if you look close. Oh, 2025. If you look in the lower right hand corner, you can see 2025 was the update. But this right here, this view has no correlation to this. This is going to be updated minute by minute. I just wanted to look at the street view of this Citi Bike bike station right here. And again, it's being picked up right here, right? And that's what we just saw. Broadway and Washington Place. And these bikes are going over here to 2nd Avenue and East 6, okay? So again, that can hold 69 bikes. The inventory right now is 13, so they're way down. I don't know what 69 minus 13, 3, 53, 43. So they can hold 43 more bikes. And again, you don't want to put all 43, but you want to have it pretty balanced, right? All these things should be in balance all the time. You don't want to have extreme excess and extreme like withdrawal of bikes or extreme lack of bikes. It could be lack of bikes. Let me look at one more. I'm going to wrap up the video here pretty soon. So 2nd Avenue and East 6th Street, that's what it looks like. This is a folium map. I told you I'm a big fan of these things. I like that a lot. So 2nd Avenue and East 6th Street. Let's look for that. 2nd Avenue. Again, I'm just looking for the bike station at this point. That's it. I'm not expecting any kind of real-time update data or anything like that. Citi Bike, I already see the image right there, right? It just popped up. So I see the station. And spin around and see if I can find this thing. Where is it? 2nd Avenue, East 6th. So was it moved? Did they take this thing out or what? Because I saw something on that map, but maybe they took it out because of construction. It looks like it was probably used to be there. Go back here. Okay, if I zoom in a little bit, where I put my mouse, it's the East Citi Bike, East 2nd and 2nd Avenue. So maybe there's some construction and they temporarily removed the bikes. I'm not sure what that is. Let me go back here and just look for one more. I think it's fine. Okay, so this is saying Mercer and Bleecker Street. Mercer and Bleecker. Let me look for that. Mercer and Bleecker. Didn't ampersand. So we should see a Citi Bike station over here. I see it right there. Okay, so that checks out. Okay, we just validated that one. That looks like that is probably northwest corner of the street, I'm guessing. And there it is. Okay, so that is good. That's very good. And that is telling me it's going from here. We have a surplus of bikes, capacity 67, 56 there. So down what, 11 bikes. And this one, so we have a surplus or the excess there. This one is lacking. And that looks like it should have up to 42 and you only have 6, right? So you could take another 6 and 10, 32, 33, 34, 35, 36. They could have take another 36 bikes. So the bike truck or whatever the thing is called, the bike transfer vehicle is going to pick up a bunch of bikes and send them over there. And it's recommended to get 18 bikes over there. Again, we don't want this at 42. We want it balanced in between, something like that. And then want to check this address on Google Maps. So East 4th and 2nd Avenue. So let me go over there, East 4th. And see if we can find the Citi Bike station. Let me zoom in. And I see it over there right in the corner. That looks like southwest to me. So I'm going to get the street view, put that right there, right in front and center. We should see that. Oh yeah, can't miss this right there. So I would say the thing's working, right? I think we did what we had to do. We optimized the process of moving bikes from point A to point B, from origin to destination, from the surplus to the deficit, from the donors to the receivers, from the excess to the lacking. You can call it whatever you want. It's a whole bunch of different things, right? Real-time data, real-time updates, optimization. Again, save time, save money. I don't know anybody that doesn't like to do both. I've never met anyone, as far as I can recall, that says, I really wish I could spend more money on things, and I really wish I could take more time to do whatever it is I need to do, right? That doesn't happen, right? So this is how we save time, save money, and help the end user, which is the bike renter, make them happy so we can guarantee that they have bikes when they go looking for a bike. It's actually there, right? So that's the whole goal here, and I think we accomplished that mission. So that's it, guys. I'm going to wrap it up here. Went a little bit long, like 42 minutes, probably a little bit longer than it needed to be, but I want to make the impression that I made, so hopefully everything makes sense now. Oh, there was a couple more things I want to look at before I log off. Just those other two markets, just to see how those stack up to NYC. I guarantee it's going to be a lot easier than New York, right? This thing is an absolute beast. Control Enter to run. You can see the hourglass in the upper left-hand corner. This is pretty fast now because we are not doing the massive New York City market at this point. So let me open this file, look where it goes down here to my default drive. So this is Nashville, open Nashville. Okay, I worked here for a while. This is definitely the map of Nashville. Same thing, anything that's green has a surplus, anything that's red has a deficit. So we'll pick up bikes from here. Capacity is 11, inventory 6, 6, 7, 8, 9, 10, 11. You have 5 bikes go on, but this model is saying take 4 and redistribute it down here. This is lacking bikes, capacity 14, inventory is 5. So you can see they can take 9 more bikes, right? Now that's not like critical. It's not the end of the world. You have 5 bikes. You can see the numbers are way smaller than New York. We saw 50, 60 capacities. Now you have 14 over here. You have capacity of 11 over here, right? It's a totally different market. So you have an inventory of 4. That, like, I wasn't in Nashville for a long time. I worked there many years ago. Inventory of 4 might be fine in this neighborhood. Maybe 4 people won't come along and use the bikes. But again, the model is trying to optimize the process. So if you really want to, fix this and make it better, the recommendation is to take 4 more bikes and drop them off right here. But I would be honest with you, at 4 in this neighborhood, you might be fine. You might not run out of bikes. The model is not saying, well, this might happen or this might happen. It's optimizing things. So scientifically, mathematically, and statistically, you should have 4 more bikes over there. Okay, that's what we're looking at. Let me look at one more market. So this is Portland, and they call this thing Bike Town. Okay. Control Enter. Again, this is pretty quick. It's a small market, so it's going to run fast. I'm looking at the hourglass, and it's done. Okay, so let's go look for Portland. I lived here for a little while, just in a hotel, not like buying a property or even renting it, just living in a hotel. which was free for me because the client paid, so that was nice. So same thing as before, green surplus, red is deficit, and the line in between shows you the movement from green to red. So if I go over here, okay, this thing is not cooperating. Why is it doing that? Okay, capacity 2, inventory 7. Um, that sounds a little bit weird. That might be a data quality issue. Capacity is 2 and inventory is 7. Maybe that should be 12. I don't know. That sounds weird. Let me look at this one. Capacity 9, inventory 5. That's a little bit more normal, right? So you have excess bikes. You have room for 4 more, but again, the goal is not to maximize all the bikes at one station. You want to balance this. So capacity is 9, inventory is 5. Over here, capacity is 6, inventory is 2, right? If 2 people come along and take those bikes, now all of a sudden you got 0. Some other person comes along, guy or girl, doesn't matter. Now there's no bikes, and now they're a little bit frustrated because there ain't no bikes and they need the bike, right? So that's that needs to be remediated. Oh, this one's even worse. Capacity 9, inventory 2. All right. So somebody's got to get on that pronto. And the recommendation is to move 4 bikes over there. Again, to balance things out. Here, inventory is 6. I'm sorry, capacity is 6, inventory is 0. That's a bad one, right? So some person comes along, there's no bikes. You can't even get 1 bike. There's not even one at the station, right? And this is all real time, so this could change in a couple of minutes. But what we're looking at now is a problem, right? 0 bikes available for somebody that wants to rent a bike. And same thing over here, capacity 6, inventory 0. So anyways, I'm going to wrap it up. That's it. I'm going to share all the code with you guys as always, right? So you have that. You can run that in your own Jupyter Notebook environment, and you are good to go. I'm going to save that right now. Save and export HTML, and you have what you need. I'll post the code when I post the video a little bit later today. And that's it, guys. That's how to optimize the process of rebalancing bikes in several different metro areas that have bike share systems, okay? So hopefully that was informative, educational, inspirational as well. I learned a couple things when I put this video together and did all the coding and the debugging and that. So that's my benefit to me. I learned a couple new tricks and put that in my toolbox. So that's it. I'm going to wrap it up here, guys. Thanks for your time. Thanks for sticking with it to the end, and I'll see you soon when I drop the next video, which should be ready soon. Let's see. Okay. Take care. Bye.